Also, the derivative is called with a different name, and this name is instantaneous rate of change. Why is it called so? Because from this formula you can see that derivative is limit of what we previously called average rate of change. So derivative is the limit of the average rate of change. And the limit is taken as h approaches 0, which means the length of the interval approaches 0. Now how can you interpret this? It means that the interval becomes shorter and shorter. So if you take average rate of change over various intervals, it becomes shorter and shorter and shorter, like in the previous example we had numerically. We calculated numerically. So this limit will equal the derivative. And now, how do you call this kind of instantaneous rate of change? It was rate of change over a large interval, average rate of change over a large interval, then it was average rate of change over a smaller interval, and then even smaller and even smaller. Eventually it will be like average rate of change over a single point, because when the length of the interval is smaller and smaller and smaller, eventually this interval becomes a single point. But then we cannot say it is average rate of change anymore, because there is no interval over which we would calculate the average rate of change. But how would we call it? So if this x represents time, then interval over time, we have average rate of change over a certain interval of time. But then when this interval becomes small, it becomes 1 point of time, or often called 1 instant of time. So now we're talking about rate of change over an instant of time. And so we don't call it average rate of change anymore. Instead we call it instantaneous rate of change. So the other name for the derivative, calculated by this formula, the other name for that is instantaneous rate of change. And now I want to explain you the geometrical meaning of the derivative. Geometrical meaning of the derivative. Again, geometrical means that it's on the graph of the function, which means assume that the graph of the function is given. So graph that is typically denoted y equals f of x is given. So let me draw some graph. X-axis, y-axis, and let's say that this is the graph y equals f of x. And now I want to copy more or less the same picture that I previously had for the average rate of change. So down here we have the interval from a, only instead of a to b, I want to write it as a to a plus h. So this is the interval we have, and for this interval, h is the length of this interval. So this is the length. Length equals h. And now we know that the average rate of change is the slope of the corresponding secant line. So let me draw the corresponding secant line. So remember, we find the corresponding points on the graph. So the graph of the coordinates of this point will be a f of a. And the coordinates of this point, instead of saying b f of b, I have to put a plus h, because this is my new b, and then f of a plus h. So these are the coordinates of the other point, and now we connect them together with a straight line. And this is secant line. And the slope of this secant line equals average rate of change. So this picture more or less we already had, but now I want to explain what happens if we allow h to approach 0, which means if we make this length of this interval smaller. So now let h become smaller. And that means that instead of the interval from here to here, we will consider a smaller interval, for example, from here to here only, like half of the original length. So this will be my new h. Let's say this is my new h. So the new h, the new length of the interval is twice as small. And then the beginning of the interval will still be the same, so it will not change. But the end of the interval will now be at this point. So this is the new a plus h at this point. Let's see what happens on the graph. So this point will lift to the graph, and this position here will be the new a plus h f a plus h. So it's like thinking that this end, right hand end of the interval moves to the left until it stops here, and the corresponding point on the graph moves along the graph this way until it stops here. And the question is now, what happens to the secant line? Secant line will now connect this same point with the new point, which means it will now be like this. So this is my new secant line. New secant line is now located a little bit sharper, so the slope of this line is a little bit higher. Okay, and now let's continue this this process some more. Like, let's say that we make this interval even smaller, which means my new h will be like this now. Let's call it newer h. So now my interval will be like this. This will be a plus h, newer a plus h. So from here to here, now it will move even further until it becomes even smaller. What happens on the graph? On the graph, this point corresponds to this point now. So it's like, again, think of it that way. This point on the graph moves even further down and until here. And what happens to the secant line now? So this position here, it's like newer a plus h, f a plus h. And what happens to the secant line? So secant line will now connect these 2 points. So this first point will never change. But the second point where secant line crosses the graph will be moving, and now it is here. So the secant line will be even sharper, so it will go more or less like this. So this is like newer position of the secant line. So you can observe that the secant lines actually move from original position. It's like kind of rotating around this point, becomes a little bit sharper, and then it rotates even further up, becoming even sharper. Now here is the question. If I continue this process more and more until this interval from a to h plus h actually becomes smaller and smaller until it becomes 0, what happens to this secant line? You may argue that this secant line will move higher and higher and higher and higher, but the question is, up to what position will it move? Where does it stop moving? So would it move all the way to vertical, like this? And the answer is no, it will not move all the way. In fact, it will move to certain position and not more. So what is the limiting position of the secant line? And if you think of it, limiting position of the secant line will be something like this. So it will move just a little bit more, maybe like this, and not beyond it. And this new limiting position is actually tangent line. Now, tangent line to the graph, which means it's the line that goes like this. It goes along with the graph, and it will never, a secant line will never go beyond that. It will only go to this position. In fact, this word tangent line is also a Greek word. It means touching. So, in fact, indeed, tangent line doesn't cross the graph. It touches the graph at one point and then goes on. So, tangent line. So, here's what we can deduce from this graphical experiment. So here's what we can tell. As the lengths of the interval become smaller and smaller and smaller, then the secant lines actually move until they approach and eventually they become the tangent line. So let me write this down. So here is the observation. As the lengths or lengths of intervals become smaller and smaller, so the secant lines will rotate and eventually become the tangent line. And this is a very important observation. Now I want to make the following conclusion from this observation. Since the secant lines rotate and eventually become the tangent line, secant lines rotate and rotate and rotate and eventually become the tangent line, so the slopes of secant lines will eventually become the slope of the tangent line. The slopes of secant lines eventually become the slope of the tangent line. So slope of secant lines eventually become the slope of the tangent line. And now I want to express this conclusion in mathematical form. So I will have to erase this picture. How can we express it in mathematical form? First of all, slopes of secant lines is something, so using math notation, the slopes of secant lines is something that we know how to express using mathematical notation and formulas. It's just f of a plus h minus f of a over h. It's the same as the average rate of change. So that's what the slope of secant line is. Now, eventually become, we're talking about the limit. So there is a limit in front of that. And exactly what limit? When we set up limit, we have to say something approaches something. And now it says lengths of intervals become smaller and smaller. Using proper notations, it means that h, which is the length of the interval, approaches 0. So this is how I translate the phrase slopes of secant lines eventually become. They become this. And now they become what? Slope of the tangent line. Now the last portion of this sentence I don't want to translate, I just say equals slope of the tangent line. So here's what we got, and now the left hand side of this equation is the same as the derivative that we already have defined, so it's the derivative, and the short notation of this derivative is f prime of a, And here is what we got, that the derivative equals the slope of tangent line. And so here is the geometrical meaning of the derivative. So, derivative f prime of a equals the slope of the tangent line to the graph of the function y equals f of x. And if we want to be more precise, we can express exactly what point, at what point. It was at the point a, f of a. Or sometimes we just say at x equals a. So here's the meaning, geometrical meaning of the derivative, that the derivative equals slope of the tangent line.